deposit of the mine is such that it has sedimentary rocks with a resource base of 50 million carats, grading 1 carats per ton. The potential life of mine is about 20 to 25 years, and the production of the diamonds is about 2 to 2.5 million diamond carats a year. The design of the mine is an open cast mine, and the cut-off grade for the mine is 0.01 carats per ton. When we talk about diamonds are usually mined in 3 places, or so to say that they are found in 3 sorts of places, mainly alluvial, kimberlite, and marine base or offshore mining. When we talk about open cast mine, we can clearly see that it's a kimberlite that we are mining. The blasting patterns of the mine is such that the largest particle size, it's 250 millimeters. It has been shown that the diamond varies with size fractions of about in the range of -3 millimeters and 30 millimeters, as saying about 0.005 and 0.006. This is just, it's like a normal distribution with the particle size on the x-axis and the grading on the grading on the y-axis, giving a normal distribution, which means our highest grade will be particle size around 20 to 17 millimeters. Okay, design task. As I said, our aim is to design a flow sheet, to come up with and to select the proper equipment.
We can't hear you. Zita, can you tell him?
Oh, is everything okay now?
Yes.
Okay. As I was saying with the design task, we were tasked to come up with a flow sheet, select proper equipments, do mass balances, and the power ratings for our equipments. We are designing the mine based on mineral processing. So we go from comminution to scrubbing, then smoothing separation to recovery using X-ray sorting. Okay. Every process has its tailings facility or waste products. The waste products will be sent to a thickener and pumped to a tailings facility, which is about 12.5 kilometers away from a 5-meter vertical inclination. Okay. The approach, as said in the design task, crushing here we deal with the size reduction, mainly crushing. Milling will be part of it, but in this case, we don't consider milling because our size fraction can be handled by a crusher. Scrubbing. The main purpose of the scrubber will be to remove the fines. Using a scrubber with a trommel screen, which separates the fines and sends the coarser materials to the dense medium separation. The dense medium separation separates the materials based on the specific gravity of the material. When it goes to the recovery, we use X-ray sorting. This uses X-ray fluorescence, magnetic susceptibility, and crystallographic fluorescence. This is calculated based on the diamond-specific properties, which separates the rough diamonds from materials that have higher density, specific density. The thickener is materials are thickened with flocculants and pumped to the tailings facility. That's basically our approach in this design. Okay, coming to our comminution stage. Comminution basically is just the reduction of particles such that the mineral of interest is liberated. To access our mineral of interest, particles are crushed to the and basically just liberated. We do this using crushers. In most cases, the widely used type of crushers are jaw crushers, gyratory crushers, impact crushers, roll crushers, and cone crushers. Okay. Crushing mechanism is usually by impact, compression, and attrition. Attrition is not really that much into crushing, but when attrition is the main means of crushing, would be a mill. I'm not going into details with the mills because I don't think they will not be used in this process. So just to talk about the mills, we have ball mills and rod mills, and they could be autogenous or semi-autogenous. When it comes to designing the comminution circuits, there are usually two approaches: the open circuit, or we can opt for usually three. I mean, the open circuit, closed circuit, or the combined multiple stage open and closed circuit. The open circuit is usually just crushing minerals, but they will have a wide range of particle sizes. But when you use a closed circuit, we are controlling the particle size distribution and keeping it in a minimum range. Factors to consider when designing. When it comes to crushing, we have to consider the equipment which you are going to select, and as well as the energy required for the particles to be broken down. Okay, Daria. For particles, the energy required to break a particle has been described by Bond, but in case when we deal with crushers, the Bond equation doesn't really do the job. So another equation has been derived it is similar to the Bond equation, and it is shown in the screen. The symbols and their meaning, like the P is for the 80% passing rate or passing size feed, and the P is 80% size of the products. The K is a constant of the ore characteristics, which is usually calculated using experiments, not experiments, but tests, like the pendulum test and the dropping test, which is incorporated in the formula to come up with the with the constant. When you see in the bond formula, it's similar to the work index. In this case, we call it the bond crash index. Okay. Then Mr. Jonathan will take over from screening.
Good morning, everyone present. My name is Chris, and I'm going to go through the screening part of our design proposal. So, the importance of screening in the diamond industry is that it is very, very important because diamonds occur in, as stated in our problem, that the diamonds in this problem occurs between the size of 3 to 30 millimeters. So, if you can harness or can get that class of material, then it's sort of like you have concentrated your valuable already, your valuable, which is your diamond, because it occurs in that size fraction. So if you can crush your material and screen it, remove all the particles above the range in which the diamonds occur, then you basically remove just gangue, because the diamonds in this specific ore doesn't exist outside the range. The other thing is, if you do your screening and you remove your, let me say, your fines, it helps because diamonds are sold by the size, so it won't really help if you reduce your class fraction, which will mean that you will have a lot of fines in your stream, and these fines will be detrimental to your downstream process like the PMS and such. Another thing is, the aperture size should be selected partly because it doesn't mean that if the diamonds in this ore occurs between the range of 3 to 30 millimeters, that we should use that as our target size fraction, because we will bring along a lot of gangue, because as Dila already explained, the diamonds are distributed in a nominal fashion. So your diamonds will be more concentrated in the middle part than to the more extremes to your left or to your right, which means the more you go to the smaller side, you will recover more fines, but then there will be more gangue. And the same goes to when you try to recover larger particles. You may recover larger particles, but then that will mean that you'll have to recover a lot. I have to take a lot of gangue with it as well. So I just want to make sure, is everybody hearing?
Yes.
Yes.
Okay. Okay. So then, what I'm trying to say with this literature review is that the screening process is very important, because it's sort of like it's actually a concentration process, because it removes a lot of gangue and it has to be selected carefully. Okay, so I think we can continue to the next slide. Yes, this is the formula that will be used to calculate the efficiency of the screens. Because we are working in the diamond industry, our screens should be very efficient, especially when you are coming to the where your error should be very little. Then you should work with a high efficiency screen, a screen with a high efficiency, because if you work with a screen of efficiency of 80, you have a better chance of losing a diamond, and we all know what one diamond is worth. So in the screening process, the efficiency of our screens, which we are going to use, is very, very important. And this is the formula which will be used. The formula is the work of the people who did the work and came up with the formula is Leonard and Osborne. Yes, they are the people who came up with the formula. And then In the picture, we only have the grizzly, and then we have the other two screens which will be used in the middle of the flow sheet, but it will be better explained in the flow sheet. I think we can continue. This one should be the same as the other one. I think we can skip this one because it's the things which I already spoke about.
Okay, good morning, everyone. I am Dorian Angwe. So I will be discussing the dense medium separation stage. As you all know, dense medium separation basically uses the specific gravity differences of different materials. So that is the principle that we will be using. And that is also illustrated in the image below, which shows that the feed which enters has materials of different densities. And while working in that piece of equipment, you have a fluid medium that has a density between the densities of the different materials you're trying to separate. Therefore, you will be able to separate your sinks, which is your material with a higher density than the set point, and then your floats, which are the materials with a lower density than your set point. We can use, in order to determine the amount of ferrosilicon or our medium, we can actually use the equation given in the, as you can see right there, the CW, where CW is your percent solids. This then uses the density of the solids, S, the density of the medium, D. Therefore, you can calculate the, once again, your percent solids. You can then use this value of your percent solids to determine your amount, your mass flow rate or your phase C that you require. The equipment that we will be using is a cyclone for dense medium separation. This is because it is given a very sharp separation at any density and therefore increases the efficiency of the process. Yeah. You know,
Yes. Can you hear me?
no.
We can't hear anything. All right. Can you hear me now?
Yes.
Yes, I think I had a problem with my speaker. So once again, good morning, staff members and fellow colleagues. So my task was to design a thickener which would handle our slurry and water recovery. So as we all know, in most operations worldwide, we treat on a daily basis a bulk of material, and most of it goes to tailings. Now, before we send this specific bulk material to the tailings, we need to treat it. And this is done by thickening and removing solid materials from the liquid materials. And by doing this in terms of thickening, we had an advantage of recovering water, and thus we have a water management that is put in place. And then this would reduce also the volume that you are sending to your tailings storage facility. Now, in thickening, or rather to say sedimentation, what you are doing is you are trying to separate liquid from solids.
from the upstreams so that it doesn't affect the downstream. And thus, we remove our liquid in the overflow, and then we would have our underflow, which will have a thickened product of usually 55 to 65% solids. That's the optimum solids that we would want to have in our underflow, and then we pump it to our tailing storage facility. Doreen? Next. Now, the operation of the thickener, it's quite simple, reliable, and effective in terms of the design setup. Once the right test work has been carried out in terms of how we would want to run our plant at a larger scale, we would then have a perfect design approach on what size our thickener will be, and thus would help in solving this huge volume that would send to the tailings. So, in simple terms, we would want to have a clear solid liquid interface in our thickener, whereby we recover our water in the overflow and the solid particles that have settled in our flow. The thickener a rakes mechanism, and this just assists the thickener with the material that is settling down so that it can move it close to the discharge, which is now our underflow, for us to recover as much as possible solids to our tailings facility. Now, to enhance our settling rates, one would have to add some reagents, and we have two types, the flock and the coagulate. Now, it depends from what type of operation you would want to run, and from your test works, then you'll be able to determine whether you need both the flock and the coagulation. So in this type of operation, the diamond recovery, we are dealing with a sedimentary type of rock. So then it will be, now with the test works that will be carried out, it will be advisable to carry out both the flocculation and the coagulation. Now, normally the flock that one would use to separate the solids from the liquid would use the synthetic flocculants. These are normally polymers that comes in different types. You find polyacrylamide and polysaccharides. Now, in terms of deciding which type of flock to use, that would now depend on the ore type that you are treating. Now, you would now look at the characteristics of the flock, whether you would want to use the anionic or cationic, and this is in terms of the surface property of your ore type now. So the physical characteristics of the flock has a strong influence on the settling of the sludge. You can continue. Continue, next slide.
Okay, my name is Joseph Zita, and I'll be talking about the recovery circuit. So, your diamond-rich concentrate is put through a series of separation technologies that may be based on the properties of the diamonds, which in this case, the technologies that they use are your X-ray luminescence, which is based on the ability of your material to emit light. Then you have your X-ray transmission, which is your XRT, magnetic susceptibility, hydrophobicity, which then they use grease tables, and then your crystallographic laser fluorescence, among others. Now, for the purpose of this diamond process, we opted to use X-ray transmission in our recovery circuit.
Hello, excuse me. There is an interfering noise. If there is, could we just put our mics on mute, except for the speaker?
Okay. Okay, so for the purpose of this diamond process, like I said, we decided to opt for X-ray transmission. The XRT sorting is increasingly becoming our preferred recovery technology in most diamond and in other mineral flow sheets as well. If we look at gold, for example, where they've also opted to adopt this technology based on the work done on the diamonds. Like, for example, if you look in Namibia as a whole, NAMDEP or the beers have started with the XRT machines, and a gold mine like Navaja, for example, they also adopted the same procedure for their recovery based on at the DMS circuit now, based on the work that has been done at NAMDEP. So, Dorian, next slide. Okay, so the selection of our X-ray transmission technology lies in the advantage of material presentation. If you compare your XRT with your XRL and these other optical technologies that they use for separation, your XRT does not require, it does not really care about dust being present, and it does not really care about how the material is presented on in the system itself. So fluorescence, if the diamonds really do have that fluorescence as a property, that won't really matter because your XRT is dependent on the atomic number of the material. So the ability and the effectiveness of your XRT is based on that difference in atomic numbers of the materials that you want to separate. So what this machine does is it works on a principle of the ability of the materials to absorb that X-ray radiation. So since your diamonds are primarily made up of carbon, which has an atomic number of 6, because it is a very light element, it will obviously absorb less X-ray radiation as compared to all the other elements that might be present in your feed, which might be your calciums, your magnesiums, and stuff like that. So you're varying your X-ray energies allow the machine to discriminate between various materials based on a combination of density, thickness, and elemental composition. This was said by Sussman, Detlefs, and van der Westhuizen. Just to show that there might be a case where you have different diamonds based on different thicknesses. Now, your machine is actually designed then to account for that by having different X-ray energies. So as soon as there's a difference in thickness, then it will be able to still detect the diamonds as from your other material that might be present. So a typical large diamond recovery process would then also opt for your XRT machines because it has the ability it does not really damage your large diamonds there. Especially if you look at the type 2 diamonds, because your type 2 diamonds are diamonds that are prone to damage as a result of being too brittle. And also they do not luminesce due to the low nitrogen content. Now, the thing about your luminescence is that your diamonds have a carbon lattice with nitrogen atoms present as well. Now, these nitrogen atoms are responsible for giving that luminescence. Now, if you look at your type 2 diamonds, they have a very low nitrogen content, meaning that you won't really, luminescence will be a problem in that case. But your XRT does not really worry about luminescence because it detects all types of diamonds. The other advantages of your XRT is that as far as automation is concerned, very little handling is required. It simplifies the diamond recovery process while significantly reducing your operating costs, and very little water is required as well. Like I said, the issues of dust and slime does not really affect the whole process. It is environmentally friendly and it is efficient for all diamond types. Next slide. Next slide, Dorian. Okay. So for the recovery circuit, we've decided to go for a two-stage recovery route plus a reconcentration circuit to further upgrade your diamonds. In this case, then you are getting rid of the majority of your waste that might be in the concentrate given to the recovery circuit from DMS. So based on the development of the De Beers technology and the work done at NAMDEP, they have opted to use, and our process has also adopted this, where the use of the CDX machines, which are basically just X-ray machines for our two-stage recovery, while for the reconcentration circuit, the single particle sorter machines will be used. So the advantage of these two equipment is that they are spillage free, and then they are self-testing, so they have their own online calibration system. They are operator and maintenance friendly. They are complete operator safety. You have low operation costs, and these machines can be controlled via SCADA interface. So for your CDX machines, they have an efficiency of about 95%, and your single particle sorter, the efficiency varies from about 97 to about 99%. Next slide. Okay. So these are the example of the machines that will be used. The picture on your left, on the left side of your screen is what is known as your CDX machines, which will be used in a two-stage recovery. And the picture on your right is now your single particle sorter, your Raven machine for reconcentration, respectively. Dorian, we can't hear you.
Doreen,
Okay.
Doreen,
So,
can you please
so can you
go
hear
back
me?
to where you started? We couldn't.
Yeah, this is
hear
where
you.
I started.
Is this where you started? Oh no, on this one.
Yeah.
Yeah, start there.
Okay. So basically, due to the 1 carat per ton grade, we can see that there are 250 carats per ton of diamonds in our feed, and that gives us a flow rate of 250 carats per hour. Our fresh medium, which is our FESI, is added at a feed rate of 3,050 tons per hour, with a water volumetric flow rate of about 950 meter cubes per hour. Our tailings, that shows that most of our gang is leaving our dense medium separation circuit. However, we can see that there are some ferrosilicon losses due to the loss of ferrosilicon in our tailings, and we also lose some water to our tailings. Other than that, the rest of our water in our ferrosilicon continuously recirculates in our dense medium separation circuit due to recovery of the ferrosilicon with magnetic separators. As you can see, our concentrate has diamonds, which we assume that there's 100% recovery of our diamonds, and that then gives us 250 carats per hour of diamonds in our concentrate as well. However, there is also some gang in our concentrate, but that's what the X-ray recovery will sort out. Joseph?
Okay, yeah. Next slide, Dorian. Okay, as far as the mass balance for your recovery is concerned, so Yes, hold on. Hello?
Hello?
Okay. Yeah. So as far as the recovery circuit is concerned, this is actually, yeah. So we receive the material from your DMS concentrate. So what happens is that your material then goes through a sorting screen where it will be separated based on the sizes. So because for your primary circuit, you'll be using two machines, with one being the coarse machine and the other being the middles machine. Your material of
Hello?
about plus, hello?
Hello,
Yes, sir.
Mr. Zita, there is some background noise each time you speak. I'm not sure where that is coming from.
Okay, let me sort that out, sir.
Please.
Okay. So yeah, like I said, we then have our coarse machines which will operate with a size of about plus 15 to 30 to minus 30 millimeters. We then have our middles machine which operates at a size of plus 5 to minus 15 millimeters. Your underpin of that double deck screen contains material of the size range of minus 5 millimeters, which will join the reject streams from your secondary middles, secondary coarse machines, as well as your reconcentration machines, the single particle sorters. So all those rejects will join the underpin material from your double deck screen, and they will go to a concentrate dump where they will be used for future references, because they do still contain some diamonds, even though it's just a small amount, but we can't throw away any diamonds. So at some point they will be used again. So from your coarse and your middles primary machines, your accepts, or which are now your diamonds in this case, will go to the middles and the coarse bins respectively, where the rejects from those two machines will then go to your secondary XLT machines, your middles and your coarse machines. So the two accepts from the two machines will now go join the other material or the other diamonds in the middles bin and the coarse bin respectively. From your middles and coarse bin, your diamonds will then go to your single particle sorter, whereby since single particle sorters work in a range of about 97 to 98% recovery, they will recover most of the diamonds. And then getting rid of the last gang material that might still be present at that stage, because your primary and your secondary XRT machines get rid of most of the gang eventually. Yeah. So from your single particle sorter machines, your accepts, which are now your diamonds, that are now free of any gang material that might be present, those diamonds will then be cleaned and then they will be packaged. So yeah, Toya, next slide.
Joseph.
Okay, so as far as the sectional managers are concerned, we have, like we said, we have 5 sections, which is the DMS. It will be, the manager for the DMS will be Dorian Hangwe. For the X-ray recovery, it will be myself, Joseph Zita. Communication will be Abram Dila Dila. Scrubbing and screening will be done by Jonathan Christian, and the thickening will be done by Henok Hakala.
Hello, who is next? We can't hear.
Dila.
Dila?
Oh, okay. Can you hear me now?
Yes.
Okay. Since the blasting pattern is such that the maximum particle size is 250 millimeters, it's never a guarantee that you'll always get 250 maximum particle size of 250 millimeters. So we'll put a grizzly at the beginning stage. The grizzly fits the jaw crusher, and if we assume that the jaw crusher reduction ratio is about is 1 to 3, so we expect particle sizes of about 85 millimeters, which we stockpile. From the stockpile, we screen the fines. Not the fines, but particles less than 22 millimeters will be sent to the scrubber or bin. The particles above 22 millimeters will be stored in an O-bin that fits the crusher, the cone crusher. And if you assume that the reduction ratio of the cone crusher is 1 to 5, we expect about more or less 20 millimeters of particle size. The processes are not always efficient, so there will be certain particles more than that, so we recycle it again, feeding the cone crusher or bin, which puts it in closed circuit. Particles lower than 22 millimeters will be sent to a scrubber bin. The scrubber bin feeds the scrubber. Since the scrubber is sort of a screen, we in this flow sheet we just put a screen just to show that the scrubber is sort of a screen, which removes the fine, and the fine goes to the thickener, and the other materials, which is more than 5 millimeters, fits the DMS circuit. Yeah, and that's basically the flow sheet for the combination.
Can I speak on the screens while we are on the same slide?
Yeah, you can do that. You can do that.
So. Okay, so I'm back on the size range of the material in which our diamonds lie. We said our diamonds lie in the size ranges of 3 to 30 millimeters. It doesn't mean that we have to use that as our, or we have to recover all the diamonds, because towards, as already mentioned by Dila, the distribution of our diamonds in our ore is like it's a normal distribution. So towards your extremes, which is like towards your fines or towards your bigger particles, your concentration of diamonds decrease, while in the middle part, let me say from 15 to 20 millimeters in size, those particles are the most. So we have to adjust our target fraction in such a way that we don't bring in too much fines into our not too much fines. We have to adjust our screens such that we don't bring in too much gang material. So we don't want to be treating a lot of gang. We just want to keep the maintain to our tons per our flow rates. So that's why it's important that in the beginning we have a grizzly, but the efficiency, not the efficiency, the separation efficiency of the grizzly is not that important. What's important is the separation of efficiencies of the screen, the one that comes from the stockpile, and the screen which handles the underflow of the cone crusher, because this make sure that we don't handle material above 22 millimeters, because there's hardly any chance for you to find a diamond there, because you are towards the extreme of the nominal distribution of the diamond. So we have to make sure that we have to work with diamonds below 22 millimeters. And when the underflows, let me say the material which is less than 22 millimeter is then sent to a scrubber. Yeah, the material is first stored in a scrubber bin and then it's sent to a scrubber. The scrubber's purpose again is to remove the fines, but it doesn't mean that because we also have diamonds occurring at 3 millimeters that we have to try to recover that as well, because when the diamond is smaller, it loses a little bit of its value because the weight of the diamonds also plays an important part in when when people buy diamonds. So yeah, so the scrubber is actually a wet process. It washes out the fines. It's water is sprayed throughout the scrubber, and what I found out is that the scrubber is actually very, very important in the diamond industry, and it's just basically a cylindrical screen that is revolving and it's sprayed with water, but it's important to the diamond industry because we don't want to be having too much fines going to our dense medium separation stage, because it will interfere with the sharp separation of the material. Yes, and also it will give difficulty when you have to recover your ferrosilicon and such. So if the fine material which already has low value because of the lightness is causing problems to our DMS circuit, we can choose a size, our cutoff size in such a way that we don't introduce too much fines in our DMS circuit. So yeah, that's about it. On the screens, I just wanted to emphasize the point that we have to have high efficiency screens because we are working with diamonds. We can't be using low efficiency screens because then we won't have control over the situation, and the diamond situation is a very delicate situation since it is so expensive. Yeah, that's about it from my side on the screening on this slide.
Okay, so for the dense medium separation, this is basically, how should I say, a simplified illustration of the diamond separation process that we will be using for the MS circuit. This is an illustration of welds. Okay, so please bear with me as this is a very loaded flow sheet. As you can see here, that I indicated in the orange, that is basically your flow of your diamond material. So as you can see, your diamonds enter through the first flow stream and goes to the mixing box, where it is then mixed with your ferrosilicon. That is then pumped to your DMS cyclone, and then your sinks go to the sink screen, which then retreat to the concentrate bin. On this flow sheet, what you can see here is basically the purple, which indicates your flow of your gang material. Once again, it enters your mixing box, which is your main source of your gang in your process, and then goes to the DMS cyclone. However, due to the not so 100% efficiency of your DMS cyclone, you have separation of your gang from your DMS cyclone, in which most of your material goes to your float screen and some of your material goes to your concentrate bin. This material is then, from the sink screens, some of the gang material is then sent to the dilute sump, where that is pumped to the primary magnetic separators, basically in order to recover your ferrosilicon. Your gang that is not sent to your gang is then sent to your secondary magnetic separators, which is then also sent to your effluent sump. The red, as you can see here, this basically shows your flow of your ferrosilicon in your system. As we can see all around the entire system, from the DMS cyclone to the correct medium sump, there's a recirculation of your ferrosilicon there, and also your recovered ferrosilicon from your float screens, which is basically recovered in your dilute circuit by your primary magnetic separators. However, as I indicated earlier, there is also losses of your ferrosilicon to your tailings. This flow sheet basically shows your flow of your water, which is also, as you can once again see, mostly recirculated throughout your entire circuit. This is supposed to be Henox. Enoch? Hello?
Wena.
All right. So this is just a simplified flow sheet about my section, which is the thickener section, or rather unit. So there isn't much of flow sheet to be designed, but what we can see here is what the solid liquid separation unit is receiving. So as we can see, the brown arrows, that is the slurry that we are getting from the scrubbing. That is now mainly with those ultra fine solid particles that we are washing out through the scrubber screens with the addition of raw water. And we send it to the solid liquid separation unit, which basically is now our thickener that is supposed to separate the solids from the liquid. We also have some fines that we can get from the DMS section. So that is now when we do de-sliming, and we also have to recover that water from the DMS section with those slimes that we get from the de-sliming cyclones. So from the solid liquid separation, then we recover water, which is now therm process water, as we feed it back into the plant, especially the scrubbing and the DMS way, because those are the two sections that mainly uses and need water for processing. And our solids, we send it to a tailings storage facility.
Continue.
All right. This is just a generic illustration of what we are feeding to our thickener. So the blue part, that is our thickener. So as you can see, we have two income streams. One showing our flow rate of what we are feeding into the thickener. This is now through the central feed well, where we are discharging our slurry and where the settling is supposed to happen from them. And then we also have a flock dosage stream that is coming in. That is now our reagents that we are adding to the thickener. So there are many ways one can add a flock to a thickener. So this is just one of the example where we add the flock from the top, but we can also add it from the sideways. And then we have our two streams that are leaving the thickener. One which is termed the overflow. That is now the water that we have recovered from the thickener. That should now be clear of these fine materials or particles. So it will be clear water. And then we have now our underflow, where we would expect to have our solids that will be pumping to the tailings storage facility. And the solids particle are in the range of 55 to 65%. Yes.
Fabian, you can go to the next slide. I think we already spoke about this. Okay, so for the metallurgical test work, For your comminution, the different tests that will be done will be your bond pendulum test, your Narayanan and Witten's rebound pendulum test, your JKMRC drop test, and then your gap setting test. For scrubbing and screening, it will be your screening experiments that you will be doing. For your dense medium separation, it will be your tracer test, your magnetic strength test, particle size distribution of your FESI, and the fines percentage test. For thickening, it will be the batch and continuous benchtop testing, small scale jar testing, and for your recovery, it will purely be tracer testing. Next slide, Dorian. Dorian, next slide.
Are you not going to speak of the equipment selection?
I don't see the equipment. It's not showing here. Yeah, now it's here. Okay. So for the equipment selection, this is basically like a table that shows the different equipments that will be used, and as well as the material of construction for this equipment, the different unit processes. So as far as crushing and scrubbing is concerned, for crushing, your primary jaw crusher, the material of construction will be your heavy steel, annealed cast steel, manganese steel. The manganese steel is basically used because the manganese steel is it's a steel that has a very high toughness. So then, in the event that at your primary jaw crushers, you have your materials which you are crushing at that stage, so you are making sure that the crusher itself does not get damaged. So then you have your bronze and hardened steel, you have your forged steel. For secondary cone crushers, you have your annealed cast steel, annealed high grade, your forged steel, your bronze and manganese steel, and your alloy steel. For scrubbing, as far as your thermal scrubber is concerned, you have your stainless steel with a rubber clad. At the screening stage, your grizzly screen will have manganese steel. Your double deck screens will be made of stainless steel. And for the DMS, the dense medium cyclones, it's carbon steel lined with abrasion resistant ceramic material. The mixing boxes will be mild steel lined with abrasion resistant ceramic material. The countercurrent magnetic separators will have the wear resistant stainless steel drum and magnets. The ore storage bin, and it's the same bins that will be used for the recovery side as well, they will be made of mild steel, while the screens in your DMS circuit will also be made of mild steel fitted with polyurethane panels. Your thickener tank will be made of galvanized or painted mild steel with a drive shaft of steel. For the recovery circuit, your CDX machines will be made of mild steel with a rubber liner. The same material will be used for your single particle sorters as well. The bulk sorting screen for the recovery circuit will then be made of mild steel.
Okay, so here we just have basic sample calculations for the calculations made in the dense medium separation stage. As you can see, your percent solids, which I explained all the parameters earlier. The CW, which is your percent solids of your ferrosilicon, should be 76.27%. Assuming 1,000 tons per hour of ore for all four streams, you're then using that 76.27%, your mass flow rate of your ferrosilicon will be 762.7 tons per hour. Okay, so
the next slide, okay. It's not showing.
It's showing.
Okay, yeah, it's showing now. So the sample calculations for your recovery is as follows. This is now just focusing on your primary section of your XRT machine. So your D, which represents your diamond flow rate, for your feed, basically the number or the flow rate of diamonds in your feed will be your feed flow rate which is at 0.625 tons per hour, which you will multiply with the grade of your diamonds received from your DMS. This will give you a diamond feed rate of about 250 carats per hour, which is the same as the amount that was received by, or it was shown by Dorian initially. So your diamonds then will be recovered by your primary XRT machine, will be that diamond flow rate in your feed multiplied by the 0.95. Now this 0.95 represents the 95% efficiency of your primary machines. This gives a diamond flow rate for your accepts from that material, from your primary XRT, of about 237.88 carats per hour. The gank removed from your primary XRT will be that gank in the feed multiplied by the 0.95, which again shows that 95% efficiency of your primary XRT machines, which gives about 590 kilograms per hour. This I believe Dorian showed initially that your gank in your feed had a flow rate of about 625 kilograms per hour. So based on the amount removed by the primary XRT, you can actually see that most of the gank is removed in the first stage, meaning that by the time this material or the diamonds reach the reconcentration stage, there will be little gank that has to be removed. And since those machines work at an efficiency of about 98%, you can then be assured that at least the majority or 98% of the diamonds can then be recovered, with the remaining 2% that will go stored at a concentrate dumped, and they will be used for future reference. So yeah. Okay, as far as your health and safety and environment is concerned, for your occupational health and safety, the site and safety induction is mandatory to all employees, contractors, and visitors. So, and it also should be made sure that full personal protective equipment should be worn at all times. This includes your earplugs, your overalls, your gloves, your safety boots, goggles, the dust masks, and the hard hat. And if you look at your recovery section, for example, you should make sure that you do not remove any covers or any shielding material unless the machine is isolated. For your environment, it is necessary to maintain the environment through adequate disposal of waste materials such as your FESI, because there might be FESI losses. So if there is such that some FESI has been lost, it should be made sure that you remove that FESI before you expose that waste to the environment. It should also be noted that that any tailings storage facility be fenced off in order to avoid causing harm to any wildlife in the surrounding areas.
All right. The economic evaluation. In every plan, operation, or setup, one also has to look at the economic aspect, which includes now the money or the capital, the startup capital that you're going to use on these specific units, which entails from your primary crushing circuit until your sorting section. So we'll be using equipments. Those specific equipments, they would be of specific materials. Those specific materials, they would also require money for purchase. So we will be looking at our CAPEX and OPEX and return also of investment. The money we will be spending to buy the specific equipments that would last for the mine, for the expected life expectancy of the mine, and how much we are going to make and pay back this the amount that we have spent on this specific equipment if we are going to have a balance in what we have spent and what we will be making out throughout the running operation. So the economic evaluation is really important, and we should keep it in mind as we decide, as we do our, as we carry out our decision on designing these specific equipments from these specific units. Thank you.
Just something quick, Mr. Dorian. Can you please take us back to the combination flow circuit? I forgot to mention certain things.
This one.
Yes, sir. Okay. What I forgot to mention in this flow sheet is why we choose the jaw crusher and the cone crusher, and why we choose to opt for primary crushing and secondary crushing. When we talk about several mines like the Namdeb, Orapa mine in Botswana, and the Russia mine in Botswana, they both uses the jaw crusher and for primary crushing. And when it comes to tertiary crushing, the Russia and Orapa mine uses tertiary crushers using high pressure rolls crushers. Okay, for us to opt for to go for 2 stages, it's that our ore is a sedimentary rock, and the characteristics of the sedimentary rock is such that it is a porous rock with low cementing power, and it's relatively it has low hardness. That's why we opt for the 2-stage crushing. And another reason would be if we go for tertiary crushing, we will be crushing our diamonds, and the diamonds will lose value due to scratching. And okay, the jaw crusher, it's an why we chose the jaw crusher is that it has a high throughput with no risk of choking, and it is cheap to maintain and operate because it has less moving parts. And if you were to consider other primary crushers, it will be gyratory crushers and the impact crushers. The impact crusher would be expensive, and the gyratory crusher doesn't accept the particles of wide ranges. And why we chose the cone crusher here, it has a high reduction ratio and a higher feed rate, although it requires particles to be pre-crushed, which happens in the primary crushing. And and the feed rate of the run of mine, it's about 285 tons per hour. Okay, then we go to the conclusion then.
Can you move to the conclusions? The conclusion slide.
Can you see?
No,
it's not.
Oh yeah, okay.
Yeah. As said in the beginning, it's a sedimentary rock, and the ore base is about 50 million carats of ore, grading an average of 1 carat per ton. The life of mine is about 20 to 25 years, and the production per annum is the expected or the targeted production of diamonds is about 2 to 2.5 million carats per annum. And our task is to design a flow sheet, select equipment, sizing them, and do power rating calculations. And making sure that the tailings are disposed safely and the mining practices is done in an environmentally safe manner. Okay, next slide, if there is a slide. Okay, and those are our references, and I think we're done.
Yes.
Okay, thank you. I guess we'll give the floor to the staff members in the panel. Just raise your hand and then we can give you the floor and you can give your comments on the presentation. All the way from the content to the way they presented and anything else, any of your observations. Or perhaps we will we'll just go in order. Okay, we've got right. Prof. Groot.
Yes, thank you very much indeed, Prof. Zinomo, and thanks to the students. I think sounds like a very interesting project that you're working on, and it was good to see the progress that you've made. One question I'd like to ask, I think it was Hinok who presented on the thickening process, am I right?
Yes.
Yeah.
Yes, Prof.
Hinok, I found the first part of your presentation very general in terms of the thickening process, equipment, etc. And the question that passed through my mind is, you're dealing with a kimberlite type material. Doesn't that have very specific requirements in terms of thickening? Thanks.
Okay, Prof. Thank you for the question. Yes, indeed, it has. In terms of the mineralogy of your ore. So, as I have mentioned, with the test work that needs to be carried out, would then have to do a mineralogical characterization to see what types of elements we have within this ore of ours, and then thus it will give us an idea of how of what type of flocculants and coagulants we will be using according to the slurry that will feed to our thickener. So that will be now in terms of now the surface arrangement of those fine materials that will is stamped as part of your gang material that will be sent to your thickener. So in terms of the chemistry from your test work, then you would have a clear idea of how one is going to use the specific type of flocculant and coagulant. Because mainly then with us expecting a lot of fines, mainly clay materials, we would then do some test work to see exactly what type of flocculants we will be using for us to remove those ultra fine solids from our slurry. Yes, Prof.
Thanks very much for that. I was just wondering, I mean, you guys are not going to get the chance to do the test work. Can't you get this sort of information from literature? Thanks.
All right. Thank you, Prof. I'm sure you guys are getting the hint. Any other questions, Prof. Groot, from you?
No, thanks. Nothing else from me at this stage. Thank you.
Okay, thank you. Prof. Msiarira, do you have any questions at this stage?
Yeah, thank you. Just a couple on the The mass balance, did you do a water balance for your, I didn't see any number. If you did, can you tell me how much of water is used per ton of milled ore and also per ton of the final product? And the same goes for energy as well.
So do you mean for a specific section or as a whole, the water balance?
When you do per ton of milled ore, so no, not
Okay.
sorry for the whole circuit, not in terms of milling, but for the whole circuit. Per ton of final product, how much water are you using?
Darren, can I answer that question?
Yes.
Thank you, Prof, for the question. So, as I've stated earlier in one of the slides, normally where we start to add water into our sections is from our scrubbers and the DMS section. And then from there, that's where we'll be getting the slurry, and it will be fed to the thickener. So now, in terms of water balance, in terms of the processed water and the raw water, so obviously we will have to have additional water supply, which is now from the boreholes in the surrounding area. And then we would definitely have reservoirs that will be storing that specific water. So then, in terms of water balance, it will depend on the plant's operation. So currently, right now, I don't have any values, but I have a generic approach to say that we'll be feeding raw water into our scrubber. In addition of that, it will be also be substantiated by the recycled water from the thickener. So in that way, I would have a clear picture on the water balance that will be circulating in these specific circuits or sections rather.
Yeah.
Okay.
Just to add to that, as you can see, the mass balance that I gave for the dense medium separation circuit, the water that's in the, what do you call it, in the dense medium separation circuit is mainly that added due to making your medium and those values I have stipulated.
Okay. Okay. Then coming to your section on the environmental management.
Sorry, Prof, there's one question of yours which was not answered at all. The energy balance.
The energy balance will be done on a later stage, because for now it's just a proposal on how we are going about the project.
Okay. All right. Okay, thank you. Then on the aspects pertaining to environmental management, you didn't talk about environment as in, it's more like the end of pipe waste management in terms of what goes to the tailings. So what about spillages within the plant? What about dust within the crushing circuit? So, and then the aspects of occupational health and safety as well. PPE is sort of, I mean, when you have exhausted like engineering methods in terms of covering the guards for moving parts and everything. So you need to amplify that. It's not restricted to PPE. And also the environment is not more like the disposal at the end, but how you manage, I mean, the unity processes in terms of minimizing wastage or through spillages, through minimizing spillages, I mean, within the processes themselves. So then you need to look up at issues that have to do with air pollution. How are you going to cater for that, for dust which will be occurring? So all these aspects have to be mentioned. So it's not just end of pipe in terms of tailings.
So what I can say with regards to the dense medium separation circuit is that there are different floors and different sections, right, in the dense medium separation circuit. So in typical operations, what we have is that on each floor there's, how should I say, a drainage system. So there are holes in the floors that lead to pipes, and those basically feed any spillages of, let's say, ferrosilicon. That would then lead back to the correct medium circuit. Yeah.
Correct.
Okay,
Yeah.
just to add on that, we have two types of operations, namely brownfield and greenfield. So these are the greenfield. These are normally new operations that are coming into a specific area. So like for our diamond plant processing, it is in the southern region, and as we all know, the southern region is termed as one of the most ecological and protected areas. So environmental studies or feasibility studies should be carried out properly to make sure that the way how we found the area should be maintained, or rather to be sustained, so that in terms of the waste management aspect, we do not destroy the inhabitants that are living there. We are looking at now fauna and flora. So these types of spillages, especially us now that we will be using reagents, especially in this dewatering section, the thickening. So that should carefully be looked at in terms of daily analysis to see how much flock is being sent to the tailings in one, and how one can reduce such discharge to the tailings. So the environmental aspect is very important and should be put at the back of our mind as we continue with our operation.
Okay, any more questions, Prof. Mseri?
No, thank you.
Okay, thanks, Mr. Selilo.
Yes, morning, everyone.
Morning, sir.
Morning, Mr.
Just to start, I thought you should have maybe given us an introduction to set the tone, so we know where you are in this kind of work and what still needs to be done, so that we know what kind of questions to ask. Because as you were going through your presentation, I had a lot of questions, because there were a lot of things that were very general. Like I think Prof. Fruit mentioned one of those. Prof. Sialera also mentions some of those things. So I think that would have helped. But what I wanted to know from anybody from your side is that what's the difference between a flow sheet and a mass balance? Can we go to slide number 24? Let's try, maybe it's 23 or 26, I'm not sure anymore. But you can already start answering this question, because I see you keep saying, okay, I think it's the previous one. You keep saying mass balance, but when we look at what you are showing us, there's no mass at all. There's no mass balance. So what's the difference between a flow sheet and mass balance?
So I was tasked with compiling the document, and it seems that I might have made a mistake with inserting the actual mass balance of that recovery flow sheet there.
You still did not answer the question.
So we understand the difference. Yeah.
Okay, we can pack that. The other one that you need to, I think, pay attention to is referencing. It never gets old. Whatever you're doing, just make sure that you reference. If I look at most of your flow sheets, you put things like a cyclone. It doesn't show where the underflow is going. It's just getting fed, and you don't see what's happening to it. So just make sure that whatever you put in your flow sheet, there is input and there's output. Is that understood?
Yes, sir.
Yeah, so I
Yes.
wanted to ask around the mass balance, but I see that I think I've heard that you still need to do that. Because so far, what we're showing us, like the one that you are showing us now, is just telling us the sizes, particular sizes. We don't see any balances there. The water that you are using, we don't see where it's going, how much of that. So I think that's what I was more interested in, but I didn't see that come. So maybe in the next presentation. I think that will be all from my side.
Thank you. Thank you for the feedback, Mr. Bernard.
Mr. Sililo.
Sililo
Yes,
Bernard.
Anything else, Mr. Sililo? That is all from you?
I think it's a minor one. When you
Yes.
go to, I think slide number 9, when you are doing such a presentation, just make sure that the language you use is proper. Okay.
Let's go to number 9.
Yeah, the last what do you call it? The last bullet point. If you could read that one for me, I struggled.
Yeah.
Yeah, the English is.
Okay, so we'll do an improvement on that one, sir.
Okay, thank you.
Yes, sir.
All right, Ms. Kurasha, do you have any questions?
All right, thank you, Prof. Good morning, everyone. Thank you, guys, for your presentation. Can you just please go to your slide on material selection, Dorian?
Just a second. Selection. Should I enlarge it, or can you see clearly?
Oh, no, it's okay. I can see. I just want to seek clarification from you on what you mean by heavy steel. I see on the primary jaw crusher material construction there, it says heavy steel. Can you just please clarify for me what that means?
Okay, I can clarify that for you, Ms. Kurash. The heavy steel, that's actually just a mistake that Dorian did. It's actually supposed to be heavy annealed cast steel.
Okay.
Yes, ma'am.
Still, that a qualification of heavy.
This is just so to say, since most of these, the material used for this is usually for frames.
Mm-hmm.
So we say it must be thick enough, or say to say just heavy. Maybe it's the use of terms.
Okay. All right. Thank you for that. So generally, okay, that was the question, the clarification that I needed from you guys. But I also think you guys should have gone. You tasked Dorian to prepare your presentation, but it looks like you didn't then go through it. There seems to be a lot of mistakes that are pointing out to him doing the work alone. So it should actually be a combined effort.
Okay, ma'am.
Okay, anything else, Ms. Kurasha?
No, that will be all, Prof, from my side.
All right, and Mr. Moongo, do you have something?
Yes, yes. I want them, Dorian, can you go to the slide where there's a communication circuit, which is having a lot of icons? I just want to clarify something. I saw if you look at the bottom there, that the icon there, it looks like a hydrocyclone, but it's written DMS circuit. Was that maybe?
Yeah, we are struggling with the icons.
But you understand what I mean?
Yes, we understand.
The slurry
Yes,
was perhaps to go to hydrocyclone first, and then maybe from there it goes
yeah,
to DMS.
Mr. Mongo?
Yes.
Yes, we're struggling with the the icons, but we'll rectify that. But as we just wanted to put the hydrocyclone there to indicate that it is the heart of the DMS section. Without the hydrocyclones, we don't have a DMS section at all, because it does the most of the work in terms of the separation efficiency for us not to misplace our diamonds and so forth.
Can I ask, are you talking about the hydrocyclone or the dense medium cyclone?
Yeah, the dense medium cyclones. Yeah.
Okay.
Yes, sir.
All right, Mr. Monk.
At the beginning, again, somewhere at the beginning in the slides, where there is like a simplified flow sheet, you have mentioned you have put up other stages like crushing. Yeah, here you've put up crushing, scrubbing, DMS, but between crushing and scrubbing, there was probably supposed to be screening there, if I'm not mistaken.
Yeah.
And okay, and again, the other thing again, I've heard from you guys most of the time the way you phrase ferrosilicon, instead of saying ferrosilicon, sometimes you guys say FESI. It's just not appropriate. It's the same as when you are saying calcium fluoride. Some people might say they will say CAF2. You will not understand what that is. If you say FESI, I might not understand. Okay, and on Dorian, I've seen the color coding you have done on your DMS circuit.
Yes.
Showing different streams. That was good. It helps with tracing, but I still struggle. You still struggle to understand what is happening because the circuits seem to be like crowded. It's too detailed.
Yes.
And there were a number of like sentences or frames which were like the font size was bigger than compared to others. Things like PPE at the end, the conclusion slide. And again, you showed a table which was showing advantages and disadvantages. I think just check on slide 20. Yeah, if you check on that table, it's the title of the table. There up there is saying advantages, but if you look at the title underneath, it's saying advantages and disadvantages. Okay, and if you go to slide 32. Okay, slide 32. Okay, because here you are saying, because if you look at the title there, flow sheet, dense medium separation. But if you look at the figure that you've put there, underneath the figure is illustration of thickening flow sheet.
I noticed that in the presentation.
Just general comments. And I think on your safety, did you guys touch on HAZOP study perhaps? Or it's still coming?
At the current stage right now, the HAZOP analysis, we have discussed about it amongst ourselves, but we are still working on it to put it on the slide for the next presentation.
Oh, okay. And there were also a number of grammatical errors, like I think somewhere you had this, I think about the slide on thickening, but then you said advantageous. The way you used that, I think we mentioned it also yesterday when you were preparing.
Okay, thank you for the correction, Mr. Mongo.
Okay, that's all on my side.
Okay, thank you very much. Mr. Titus, you are there?
Yes, thank you, Prof. Good morning, everyone. I think on slide 8, they mentioned that comminution doesn't apply, the famous bonds law doesn't apply. But when you look at that equation, it's exactly the same as Bond's law. 6/12 is 1/2. What the difference comes in with the work index, but it's exactly the same as Bond's law. It's just the work index that we don't use one for the ball mills and road mills.
Yeah, that I mentioned it. It's similar to the Bond equation, but it's not the Bond equation, the Bond formula.
Okay.
Yeah.
Okay. And then like 26, that flow sheet for the combination circuit. Oh, probably.
Yeah.
The jaw pressure discharge, I think maybe you can, I'm not sure, I'm not seeing the flow sheet. Okay. Yeah, the jaw pressure discharge. Perhaps that is minus 85. If whatever that comes out of the jaw crusher, maybe you can put a minus 85 there.
Okay, so I'll do that.
Yes, and of course the sparing there for the grizzle and the thickener on that flow sheet. And when you look at the reduction ratio, there for the jaw crusher, for the grizzle there and jaw crusher, you are using a semi-comma, and then for the cone crusher, you are using coron. Here you are using semi-coron, and then for the cone crusher, you are using coron. Maybe consistency. And then generally, I think for the tables, you are putting captions beneath the tables, under the tables. I think generally the convention is that the caption for the tables are above the tables, and the caption for the graphs, for figures are below. And generally for captions also, for both tables and figures, we don't use, we don't put full stops at the end. And on your slide 21,
sorry. Titus, can you see?
No, this is still 20, this is 35.
I'm on 21.
Yeah, but maybe 20, yeah. That's fine. I think the references, you put the references, the reference there after the full stop. You have a sentence, you put a full stop and then a reference. The reference should come before the full stop. Maybe, yeah. I think that should be enough.
Okay, thank you very much. You are benefiting from this gentleman, the designers. I'm sure you'll make note. Any staff member that I've left out? I can't see any. Anyway, thank you very much. And my apologies for delaying the meeting. I was struggling with water. We had no water in our area, so I had to do a few gymnastics to make sure that I did not. I was presentable. Okay. All right. So thank you very much, all the staff members that took part. I'm sure the students benefited a lot from your comments. And also special mention to Mr. Thomas Moongo, who arranged this. We really appreciate. And then to the students, I want to thank you very much. This is the first time we have asked people to do group work. And for you, it was particularly difficult because you was somewhere in those Welsh Bay, others were all over, and obviously you were supposed to make the best use of technology. And you are also our first group to do online presentation. So please bear that in mind, and we appreciate. But having said that, there is a lot to do, especially in your presentations. Well, let me just start with the presentation, because each time presentations are happening, we are now thinking of online courses so that people can actually pay for our courses. And I imagined you giving us an online course the way you were, and me paying. And I felt that I would be very disappointed if I was paying because you were standing up and doing that, and then there were some background sounds and things like that. It wasn't as smooth as I would have wanted it to be. So this is something that you should polish. All right. And then sometimes you may have to use background effects so that we don't see people moving backwards and forth behind you. Anyway, I've got a few questions. I know some of them I might have asked them already, but I would be very happy to just ask them again today. On the sizing, on the screening, I don't know why you picked 22 millimeters, for instance. There's a combination circuit that had a 22 millimeter cutoff point. I don't know where that came from.
Which one?
Yeah, that one. After the screening, you've got going to the scrubber bin, you've got minus 22 millimeters.
Yes.
Why particularly 22?
Why particularly 22?
Yes. Where did you get it from?
Oh, in the design problem,
yes,
we see that the particle size distribution and the grade of the ore, it was normally distributed.
Yeah, between what and what?
Between minus 3 millimeters and plus 30 millimeters.
And then why 22?
The minus 3 millimeters was like 0.05 carats per ton, and the 30 millimeters was 0.06 millimeters. Carats per ton.
Yes, that is fine.
Yeah.
And why?
When we take the where our high grade lies, it will be somewhere in the middle, but a little bit to the right.
So you are going to discard the material between 22 and 30 millimeters, or you are going to crush? Because I thought you were given specific numbers to work with.
Oh.
Sir.
Yes.
The reason why we thought, or I thought we could choose the 22 was because if you choose it close to 30 or exactly at 30, you will introduce a lot of things with the material, because your diamond concentration around 30 millimeters is very low. So it's more in the middle. So we are targeting the range with more diamonds, and we are trying to eliminate as much as possible.
Personally, I would have not worried much about taking a bit of waste to diamonds. I would have worried very much about throwing any diamonds to waste, especially the large diamonds.
It's true. Okay, sir.
All right.
Consider that.
All right. And then, of course, there was that irritating background sound, which I didn't like at all. And then you didn't mention anything to do with security issues. Diamonds security is one of the main parameters in diamond circuits, and you didn't mention anything to do with security. I don't know why.
Yes. Yes, Prof. As far as the security is concerned, I think we will make sure to mention that in the next presentation, because I think that was supposed to be part of this one as well.
All right. And then your formula for efficiency of screening, it would be nice to have the multiplication sign between those brackets of yours.
Okay, sir.
All right.
Yes, Prof.
Anyway, thank you very. Yes.
Yeah. Just to add on the security aspect, we will on the site we will have workers, obviously. So we are all human beings, and sometimes we get caught up with those extra ideas. So in terms of security, the company would make security as a #1 priority in terms of where our diamonds will be recovered, especially in the DMS section on our sync screen. So that specific area will be isolated. It will be having a locked section whereby.
Okay. That's fine. Sorry to interrupt. That's fine. Thanks very much. I just want you to address that. And then on your formula that you are showing right now, you can see that the F in your formula is a capital F, and the F in your where you are explaining is a small f, which means that they are not the same. So anyway, pay attention to those details. Once again, thank you very much. The staff will do as much as possible to score you, will do their best to score you. And you have a lot of work that needs to be done now. You have been given the guidelines, and I think you've got less than a month or just 1 month to finish if you want to graduate. But if you are not very keen to graduate now, you can always wait for the next group. Okay, thank you very much. Over to you, Mr. Mwongo. I guess you are administering. You can close the meeting.
Okay, thank you, Prof. Zinomwa. Okay, I think everything else has been said. It took some time, but I think it's fine. We can end the meeting here, unless perhaps there's something else. Okay, in the absence of that, yeah, you can have a good day.
Okay, good day, everyone.
Thank you.
Thank you.
Hi, everyone.
Thank you.